Uh, so I'm going to talk about, oh, wait, let me just check whether everything works. Yeah. So I'm going to talk about something like which many people have, which is known for many years, localization to delocalization transition. A lot of work has been done. Many experts are from here. Many people are experts here, but I'm not an expert in localization to delocalization transition, but I'm just going to address a particular topic question about this. And because this topic is known for many, many years, so I will just remind you some of the stuff. I have many slides, but I will not be spending a lot of time on these slides because most of these things are already known. I will just indicate the topic points in which I'm interested in. Okay, so localization, as just reminding the students, its absence of diffusion. More generalized definition will be confinement of a dynamical variable in a small part of available space. Many kind of localizations. You can have quantum mechanical, classical, a particle in a disordered potential, a scar. Okay. A stable island in classical phase space is an example of classical localization, standing wave, localization of energy in non-ideal spring. Similarly, extended dynamics, quantum mechanical, a plane wave, free electron in matters, classical, a chaotic trajectory. Now, why I have to say this? Why I have to use these, remind these definitions? Because in context of many body localization now, it has been revealed that there are localization to delocalization transition. There are two parts of that. One is from localization to extended states, and then from extended states to ergodic states. Okay. So let's remind ourselves, how do you differentiate between non-ergodic extended states and ergodic extended states? So first, ergodic dynamics, almost all parts of available phase spaces exist. So normally which we think that is the same as extended dynamics. No, non-ergodic extended states are if in infinite time limit, if the volume occupied by the state and volume available to the state goes to 0, is the definition of is non-ergodic extended state. An ergodic extended state if the state occupies whole of the available volume. Okay. So with this, let me remind you the scaling theory, which came, one of the writers were from here. So based on the initial values of characteristic system parameters, system flows either to the localized regime, when system size goes to increases, goes to infinity, or delocalized regime, or it remains scale independent and remains at the critical point. You also have single parameter scaling. Only a single parameter requires to distinguish between localized and delocalized phases and to characterize the localization to delocalization transition. Okay. And one example of that single parameter scaling is dimensionless conductance, which very clearly marks between the localized regime and delocalized regime. Okay. Then, but the question is, when we enter into mesoscopic regime, this single parameter scaling is no longer sufficient, because now the scaling variable itself fluctuates from system to system, and you have to think about the distribution of scaling variable. Okay. So a distribution, how do you define a distribution? How do you define a single parameter scaling in context of a distribution? So a distribution of physical quantity, x, that depends on system size L, and a set of n initial parameters, T1, T2, Tn, obeys one parameter scaling. If for large L, it is approximately a function of only x and one scale dependent parameter lambda L. This definition, I'm reading it because it is important in the context what I'm going to talk about now. Okay, so this is the definition. Initially, you have n system parameters. L is the system size. X is the variable in whose distribution you are interested in. But in L goes to infinity limit, it depends only on x and a single variable, single scaling variable, and the flow of that variable is defined by this equation. Now, how do you define critical point in this context? Critical point, a universal limiting distribution at the critical value of when lambda L, if in L goes to infinity limit, this scaling variable lambda L on which this distribution depends on takes a finite value. Okay, naturally, if this distribution depends on lambda L, and lambda L is system size independent. This distribution is size independent in L goes to infinity limit. So it will be a critical distribution. Okay. Then, now, the common sense, this slide is just common sense, but I'm just writing it just to remind, sometimes we have to remind ourselves the common sense. To connect the things clearly. A multi-parametric system represented by a multi-parametric ensemble. So distribution of a typical property of a multi-parametric ensemble, a function of many system parameters. Okay. So if a single parametric scaling of the distribution exists, it requires a mapping of the multi-parametric ensemble to a single parametric ensemble. Okay. So most of these systems, disordered systems, they have many parameters governing their dynamics, governing their behavior. So question is, and if they are disordered systems, they are represented by certain ensembles. The question is, these multi-parametric ensembles, can you map to a single parametric ensemble? Okay. And if it exists, how to find that single parametric ensemble? The answer is, that ensemble is Rosenzweig-Porter ensemble for many localization to delocalization transitions. Okay. I cannot say for all because I have not worked out all. I haven't checked all. So now, just reminding you, Anderson-Hamiltonian quantum particle moving in a random potential, and where this is the normal Schrodinger equation. VR is a random potential. Let us consider white noise in context of this talk. As we all know, it depends on many system parameters, dimensionality, disorder, hopping, whole lot of range of properties. Okay. Now, you see, if you write down the Hamiltonian, Anderson-Hamiltonian in the side basis, it turns out to be, let's take the diagonal disorder. For context, in context of this talk, take Gaussian disorder, although we know that Anderson transition is independent of what kind of disorder randomness you choose for the disorder. Okay, so you take Gaussian disorder for the diagonal elements and nearest neighbor hopping. So you see red, red color, these are zeros, that means hopping is not allowed. And these yellow colors where hopping is allowed. So depending on the dimensionality, physical dimensionality of the system, the matrix will be sparse because there will be some points will be zero, many points will be zero, some will be non-zero. Okay. Now depending on if the diagonal elements are Gaussian distributed, you have chosen non-random. If the hopping is non-random, it will be you can write down the distribution of diagonal matrix element, which is connected by hopping by this delta function behavior. And if the hopping is also random, and let us choose Gaussian, so you can write it as a Gaussian distribution. Okay. Now you see when V goes to 0, it approaches a delta function. So just by switching this parameter, you can switch between random or non-random behavior. Okay. Similarly here, if the V is a measure of disorder in the system, the diagonal disorder, on-site disorder. So if V goes to 0, this also goes to, the V goes to 0 means disorder is very weak. So this also approaches a 0 value, tendency to maximize near the 0. Okay. So now, Anderson-Hamiltonian is a sparse matrix in side basis. Okay. So degree of sparsity is fixed and depends on the dimensionality and range of hopping, but effectively sparsity increases as disorder increases or hopping strength decreases. Okay, so probability distribution of the matrix elements of Anderson-Hamiltonian can be written in this form. This represents the Gaussian disorder or a diagonal disorder. This distribution of the diagonals, and here by choosing BKL 0 or non-zero, you can control the hopping and non-hopping. Okay. Now this delta function can be written as a Gaussian by taking appropriate limit. Now why I am showing this? Because just by writing it as a limiting Gaussian, you can reduce this whole distribution of matrix element in terms of the multi-parametric Gaussian distribution. Okay. Now comes the, okay. So basically you have to study this system if you are choosing the diagonal disorder. And just by choosing appropriately these mean values and variances, you can model whole lot of disordered systems, okay, non-interacting electrons. Okay. Now this ensemble depends on so many parameters. Information of system parameters enters through these mean values and these variances. So this is a multi-parametric Gaussian ensemble. However, it is possible to show, just by if you study, it is possible to show that it can be reduced to a single parametric diffusion, where the single parameter is of this form. Okay, what is the single parameter? It contains information about all the ensemble parameters which appear here as the mean values and variances. And let me remind you, these mean values and variances contain the information about various system conditions. Okay, so what is this Y? Average distribution parameter, a measure of average uncertainty of the system, a measure of complexity of the system. Okay, so let me, okay. Now, I don't think I have much time. So what is this equation? Solution of this equation is a single parametric ensemble, and this ensemble is known as the Brownian ensemble or Rosenzweig-Porter ensemble. Brownian ensemble is a very general ensemble, but if you are considering the initial condition as the localized state, then it becomes a Rosenzweig-Porter ensemble. So this is either you can call it Rosenzweig-Porter ensemble or Brownian ensemble. Okay. So the statistics depends on a single parameter, again, which you have to rescale by the local mean level density. And that's how the information about the dimensionality of the transition enters in this problem. I could have gone, I will just quickly go. Now this was the Rosenzweig-Porter ensemble. This is actually the Rosenzweig-Porter ensemble. And as you can see, you can substitute this ensemble density or matrix element distribution in the diffusion equation I showed, and you can check that this satisfies. So this is the single parametric ensemble to which all these multi-parametric Gaussian ensemble gets mapped. This Rosenzweig-Porter ensemble has two critical points. Critical points, as I already reminded you, depends on that in size, system size goes to infinity limit. Okay, so I'll just go to the end now. Okay. There is a lot of it. So I could have shown you the numerical results, but I'll not. Okay. All kind of transitions you can talk about. I have just given you the example of Anderson transition, Anderson localization, but you could have also talked about the dynamical localization in phase space, like quantum kick-to-daughter, which shows localization in the momentum space. You can also talk about the localization which occurs if in the, let's say, Goldstone modes, when you have system, like phonons in the lattice. That leads to correlations in the matrix elements, and that also leads to a different kind of localization than the Anderson localization. I could have also talked about many-body localization, which shows two critical points, and many-body localization in the Fock space can be mapped to the Anderson-Hamiltonian, Anderson localization. And so this Rosenzweig-Porter ensemble, if I had time, I could have showed it to you, that it can model quite a big range of localization to delocalization transition. So this is what I've already said what I was saying here. So this is, okay. And then, okay. I haven't yet studied the electron interaction, the correlations among the matrix elements. Thank you very much.